Numpy, now that we've seen the basic idea how it works, there is a humongous stuff in there and a whole bunch of different matrices, like masked ones and sparse ones. But here we just use this Numpy arrays. We can only really scratch the surface. I get the basic idea, so then the Numpy reference and the scipy reference, and then all the other things that are built on top of Numpy. So you just read the corresponding reference. So let's continue with the Numpy demo. We left off with this thing that the MATLAB had, and Python doesn't have ordinary, but has there in the Numpy. So Numpy is like a MATLAB inside Python. So there you can easily also Google comparisons, one column how the MATLAB thing and then the equivalent Numpy thing. So you can now do all the things that normally would be done in MATLAB in the Numpy. Well, at least as far as I know. But anyway, so let's look at this scipy. And before that, so linspace. So this is like a classic MATLAB right here. So to create a vector with the uniform ruler points, so 10 points from 0 to 10. So how many points? So now gotta be careful. So if there were 11 points, so then the fence post problem would be easy to solve. But when you print these actual values, so notice the ruler doesn't fit in. So we have 11 ruler marks would work a lot better. And then the trick that so we make another linspace with the higher number of points. So let's see. So from the scipy, as I mentioned, it looks like a pretty much numerical math for a standard undergraduate engineering math major here. So one-dimensional interpolation. So given a bunch of sample points, then so we calculate the sample points from the linspace. Well, here in this made-up example, we know what the true underlying function is. But suppose we give the interpolation these sample points, and then tell what kind of interpolation to use. So this function, so it's a Numpy function, it can be applied to another vector. So when we apply the function to this higher resolution ruler, hopefully these results close enough resemble the results of this function that we tried. So of course this kind of sampling has to assume that this function undersampling is numerically well behaved, that theoretically in any interval, no matter how small, there could be some weird spike in there jumping to the Andromeda and coming back to our whiteboard then. And so we just, all the numerical methods assume that implicitly that the underlying functions are simple enough. So if they're nature, so nature usually is not capricious making up stuff like that. Classic MATLAB, like so clearly remember teaching MATLAB a decade ago. So this is like a straight out of MATLAB. So this create the figure, and then you make a whole bunch of different plots from your data vectors. So the matplotlib is basically the MATLAB plotting implemented inside Python. So here's another one, numerical integration. So we can try, so we make up an exact function and then try out this various numerical integrator method. So this would be presumably in some numerical optimization course be explained. And then yeah, so here is a function that can be sampled at any given point. That's nice to have if nature gives you one for your problem. But then so you just get a bunch of sample points, and then all we can do is guesstimate from there. Notice the use of floating point placeholders, point 6f to the 6 decimal places. So that we get enough decimal places to show that the guesstimation that they make from the limited data, then it's biased in different directions. Numerical optimization, so your standard minimization algorithms, you don't need a maximization because minimizing a function is same as maximizing its negation. So the rest you just from the library have to look up. Now I have another Numpy example specifically for image processing. So we have an image demo here. Now what is a two-dimensional pixel image? So it looks like a two-dimensional matrix to me. So if each pixel was a single grayscale value, so then we'd have a matrix of numbers, numbers known from some range that 0 is whatever is the darkest black that the pixel can be, and then the maximum value would correspond to the brightest white that the pixel can be. Neither of these from the color theory we know is anywhere close to what can really be dark and bright, of course. Okay, so what if you have a color image? Nothing changes. The color image is three-dimensional. It is just that the third dimension is just a bit of a knob in there. So the height and width, notice the row index comes first in these 2D structures, column index comes second, and then the depth of the image, so how many image color components. So RGB, that's the way that the computers normally represent colors, but other more human-friendly color spaces, of course the conversions are just some kind of algebra, and surely somebody must have implemented those conversions so that nobody has to reinvent that wheel again. So scipy ND image. So this is functions that operate on the assumption that the two or three dimensional image, so the matrix represents an actual raster picture. So image processing Photoshop style operations implemented, everything is just numbers, so massaging those numbers we can do image transformations. So running the example, I have here the spider. So this spider is showing the images that it displays. So hopefully this doesn't task the YouTube compression. So normally I would think that in these videos, considering that the most parts of most frames are exact same as in the previous one. Notice so here every frame is the same. It is just my voice in the sound dimension that is changing. So you think that whatever compression codec they use internally in this kind of situation would then be highly efficient. So that kind of codec, I don't know, I haven't looked into compression again in 2 decades, but if that doesn't exist, so then my entire worldview would be very shaken. But so one test image, this kind of a cute animal, so this kind of a royalty-free image. So reading through the image demo, the main part of it, so miscellaneous face, so it's like a test image there, and it is a raster image. So as far as Numpy is concerned, so it's a 768 by 1024 times the, and each of these components is 1 byte, and so then the Numpy, because you can make element to be any number of bytes, so one byte the unsigned integer, so we can directly calculate the number of bytes needed. So this is the raw image. Every pixel can be anything, so no compression has been applied. Now conversion to grayscale. This one is a good one, illustrating the Numpy universal function broadcasting. So the dot product of the image, so image is h by w times 3, and dot product with something that is 1 by 3. So this is automatically expanded over the height and the width, and the dot products are computed with the third dimension. So the third dimension, the little snub RGB values, so red gets this much weight in the human eye. I don't know where I got this, somewhere. Green, that we're more sensitive to, gets that much weight, and the blue, that we are insensitive, that our eyes gets less weight. So this the weighted brightness, and this still doesn't involve the gamma correction or any of the display settings. So I'm sure the Photoshop engineers can do this in a much more correct fashion. But let's to showcase the dot product. I remember a couple of semesters before I had this written as a Python for loop, but it feels like that whenever dealing with the Numpy array, if you're Python for looping through it, then you're given up already. So then feels like you're doing something wrong. So some Numpy Pythonist can maybe explain that, but the idea is to use these Numpy functions because these have all the hardware acceleration and parallelism that is available in there. Rotating So the conversion to grayscale, so we get the image that is 768 by 1024, so each pixel becomes 1 byte. Floyd-Steinberg dithering, so this dithering problem, take a picture containing a large number of colors and make the best approximation using a small palette of colors here implemented for binary black and white. This algorithm generalizes to arbitrary color spaces, but notice that the obvious solution convert to black and white. Any pixel brighter than threshold becomes white, any pixel brighter or equal becomes black. Creates a bunch of blotches that have no detail. So that kind of we have to maintain the color gradient by whenever a pixel value is made to be black or white. So forced to be something that it's not. It's something in between. All the neighboring pixels compensate by becoming different, and by some kind of magic, this from the 70s, this algorithm. So the algorithm as a side effect creates a kind of stipple pattern that is gonna simulate the underlying color gradient. So the way that we perceive three-dimensionality, all these images are two-dimensional, we just play along and pretend that they're three-dimensional. But if the color gradient information vanishes by turning areas into uniform blotches, so then we can no longer pretend that it's anything other than what it is. So 2D bad simulation of a 3D scene. But that's what all these are, but some of these simulations are good enough that we play along and forget that these are actually 2D images. The convolution from image processing. So it is of course so important that it is there's a whole bunch of image processing operations are the special cases of convolutions with the suitable kernel, and so this ND image convol modifies so creates a result. Floyd-Steinberg dithering, edge detection, so all this image processing stuff, break into submatrices, rotate each one, reassemble them. Pixel sorting was fashionable 5 years ago. So just sort vectors, so the columns and rows according to pixel brightness. I used to make some computational art with this, with adding edge detection that couldn't cross the edge, and sometimes it got weird results and sometimes just nonsense. But blurring. Okay, what do we have here? Image transformation. Which is there built in. So geometric transform the pixels, it's like we pretend that from the coordinates they move to a different coordinate. So transformation function with a bit of a trick in there, so creates this kind of a sine curve that waves the pixels to different directions, and the mathematics of a spiral. So notice that the transformation can be a fractal subdivision. Well, it's not a well, it's a subdivision, but then we twist the subdivision into a spiral shape. So everything is just numbers. You can do whatever you will. That's the only law.